Hello students, welcome to the session. So now let's continue the series like this 2-in-1 series in which I have started the semaphore concept from the operating system. So already 2 sessions we have taken, so you can see the part 1 and part 2. In the part 1 I discussed like a semaphore, its a definition and the framework. The followed by we have like seen in the counting semaphore. In session number 2, so I focused on binary semaphore, its implementation like so how we can see the binary semaphore operations, and also I have taken one case study like so semaphore based solution, especially in producer consumer problem, how we can use the semaphores to like ensure the mutual exclusion data consistency under producer consumer problem. So similar way I will be taking one more case study on like a reader writer problem, especially in a concurrent environment when multiple process want to like just read or update the database, then definitely bound to have some inconsistency if I allow like some process for reading, some process for writing. How we can write this semaphore based give a solution for that. So we'll observe in this session, followed by this case study. We'll also solve some couple of problems which are related to the semaphore. So now let's begin the session. So the second aspect like I say like reader writer problem is the classical IPC problem, like IPC environment where actually we can see like IPC environment where we can see that inconsistency can happen. So now see the solution for that. Okay, so let me give a problem statement. So reader writer problem, so it is a known thing only, like it's a database. If I take database, okay, so database there are 2 set of processes we can have, like readers, reader, like process is a reader, process is a reader, please understand readers, so I can write readers. Okay, then another type of process like what, writers. So writers, n number of writer process, n number of reader process can come to read or update the database, to read or update the database. Especially IPC environment, which is concurrent environment, multiple process they start sharing the what, this is shared resource, right, like shared what, database like. So process can come for, some process can come for reading only, some process to want to update the data. So we know, like suppose if I allow a reader process, you understand the reader, one reader is there, assumption, and one writer process came. Okay, so reading nothing but just reading the database. So just in between some writer came and update the data, again reader came and for reading the data. So definitely the data which you read in initially and after reading, after updation, the values will be changed. So there is a like inconsistency reading a data because in between somebody comes and update the data. You know these things especially in database environment, correct or not? So such operations, so we should be ensure like there must be some mutual exclusion to access this database like when different process comes, reader and writer. Similar sense assumption, second case. So one writer process came and one more writer process came, like a 2 writer process came. One is updated in between, like the before updation, second one another process came and updated, or again this process going to update something. So again there may be inconsistency between the processes. What I want to say, so the simultaneously one reader writer or 2 writers should not allow to update the database. So there is a what, so if you allow it, what happen, inconsistency will create it. So dear students, you should understand, to create a consistency in the IPC environment, the following condition must hold, that is, so read of ith process intersection write of jth process. So this value should be empty, meaning reader and writer should not allow at the same time. Similarly, so write of I and intersection write of j, so 2 write process also should not allow at the same time. So now read of I of ith process, another so read of j process may or may not be NP. This is not going to be create a problem. So this condition, first 2 condition must hold good. So in order to have a consistency in the database, these 2 conditions also we call Bernstein condition to create a consistency in the database. So now this is a like a what you can say problem statement. You understand, when n number of process comes for reading, we should classify what type of process, we should ensure these 2 conditions are satisfied. So now we have to see semaphore based solution for this. How we can write this semaphore based solution to like to create a mutual exclusion to access the database when somebody comes for updation. Okay. So now we classified the readers and two types of processes are there now. So what we understand again, two readers should, like reader and writer should not allow, writer should not allow, right? Reader can come, right? So meaning you understand. So if first of all one reader comes assumption, if a reader process comes, you understand. So reader process comes, so writer should not allow. Okay, second point. If one writer comes, one writer process came, so either reader or writer, please understand, if reader or writer two should not allow. One writer came, writer process one came, reader one or n number of readers or writer should not allow. This is important. Third one, if one reader came, please understand, one reader came and understand, n number of readers can be allowed. N number of readers can be allowed. So these are the things need to be noticed here. Okay. The first thing, if reader comes, no writer. If writer comes, reader should not allow, writer should not allow. So for implementation of this one, some kind of variables I am using. Okay. So there must be some binary semaphore mutex based variable required to ensure a mutual exclusion to access the database. Correct. If writer comes, no writer, reader should come. If reader comes, no writer should come. Always there must be some mutual exclusion access to what database, right? So I am introducing like no DB, like no, like DB is a variable I am taking. Okay. So DB is a variable. Okay. DB is a variable which should be what? So binary semaphore. It should be what? So binary semaphore based. So this I'll try to initialize this one assumption. Okay. This, so I am taking. So one thing like. So one more variable I am taking mutex. So this mutex variable I am taking mutex. Okay. So mutex should also initialize to 1. Why mutex is required? Why the mutex variable is required? So anyway, this DB is going to service the like mutual exclusion between the reader and writer or writer and writer. Understand now. When one reader comes, so can I allow n number of readers? Yes, allow. N number of readers allow. Meaning one reader comes, you should stop writer and it should allow the reader. So means any number of readers come for reading the database, the first process, that is a reader, first reader process is responsibility to like control the database as well as you should allow n number of readers. So I am defining the first process. The first reader should ensure to allow n number of readers without any conflict they can read, and we should stop what? We should stop what writer, right? So now, so I need to maintain how many readers comes, because I am the first reader, suppose say how many readers are there. I am trying to use one more variable called reader count. So I am trying to use RC. So initially this value is 0 assumption. So what is the purpose of the mutex? Okay. The first reader responsibility to allow the n number of readers to access. So once n number of readers comes for reading, they leaving from the database, right? And this last reader responsibility also, if the database is down, it is already down, then you should wake up, like you have to up the database. The first reader responsibility to down the database so that no writer will come when readers are reading, and the last reader responsible to what? Up the database so that either reader or writer can come for updating or reading database. This way you should so do the mechanism. That is the reason I am using the RC count, maintain how many readers are there. Now this mutex is going to be mutual exclusion to ensure like because see, when the readers are coming, they are incrementing their count, how many people came, and while leaving from the database, please understand, they should also reduce their count value so that they are leaving from the database, so that the first reader, I can say last reader. So these two readers also may be using the shared variable. This is what? RC, the shared variable. So to control this shared variable, I will be using what? The mutex is a binary, the semaphore mutex initialized to 1. So by using this one, so we can start writing the code. Let's understand the code here. I'll declare global variable int RC equal to 0. Okay. So this maintain the reader count. Okay. Reader count. How many readers came like this? How many reader count now? So another variable what? Binary semaphore, right? Binary semaphore, binary semaphore, that is mutex. Okay. Mutex. So this is initialized to 1. So this is going to ensure, okay, ensure the mutual exclusion. Okay. So between readers to access the count variable like this. So another binary semaphore variable, binary semaphore variable, db I am taking, db I am trying to initialize 1. So this indicates to ensure mutual exclusion to access the database, okay, okay, between what? So I process, reader and writer are getting my J process, or you understand? So writer and writer J, like this, either two writers or reader and writer. This is going to ensure the mutual exclusion. Okay, I initialize this one. Okay, look at the code here. Look at the code. So first I would like to write the code for writer process. Okay, so writer processes. Okay, wide. Okay, wide one, like the wide. So writer code, I am writing like writer code. See, this is for writer code. Okay, now understand here. So reader writer is continuous process, right? So I can write it while 1, n number of times this can run like this, while 1. So or you can if you are not keeping also, suppose example, so writer process comes, n number of writer process, they can run this code assumption. Okay, what is the first step here? What is the first step? What is the first step for the writer processor? So to update the database, suppose here is a database, so you have to perform the down. Okay, you have to down on what? So db, down on db, like, so let me make it like down on db. So this operation, down db value 1 down 0 successful. So they can access what? Critical section. They can access the critical section. This critical section is nothing but what? Updation of the database. You understand? Okay, once done, then they can perform upon this db value. Okay, upon this db value, then they can leave it like this. Can be even, so if you continuously want to read it, you can put it while, or you can write it for one time on also, you can write it. This is the code for the writer. Simply the writer process has to come down the database, like down db means what? db equal to 1 down 0 successful means what? No writer will come, yes or no? No other writer will come, and our reader also will not come. Like once writer is enter, you should not allow other writers as well as the readers also, right? That's what db are maintained. So once your updation database over, you can just update database so that other writers or reader can come. This is the code for the writer. Similarly, you see for the code for the reader, so reader code, reader process code, understand? Okay, so wide, okay, wide. So I can mention like a reader like this. Okay, you can also wide write also can write it. Okay, now see what the reader code should have. So as I mentioned, the first reader responsibility to like down the database, and down the database nothing. Once first reader comes, no writer comes. No writer should come. That means you should down the database, and you should allow n number of readers, right? So we maintain the RC is a global reader count, right? The first step, you understand reader, you should increment RC equal to, like I'm writing first statement, you should increment what? RC equal to RC plus 1. Why, sir? Why should I increment this RC value? Because to know I am the first reader or to know the last reader. To increment this one, this incrementation, the RC is a shared variable between the readers, right? To increment this one, please understand, again, this is what shared variable should be, keep it as a like critical section. So through binary semaphore operations only should do it. So first operation I should perform. So first operation I should perform, understand, down on. So down on mutex I'll do, down on mutex. So down on mutex, understand? Okay. The second operation now, RC equal to RC plus 1 I am performing, right? The third operation, understand. So mutex will initially 1 down 0 successful, so that no reader will come or no writer will come. Like anyway, writer I did not have, but no reader will come immediately. Okay, because you should down the database, right? So I'm writing third point, you understand here. If RC equal to 1, what does this line says, As a point I told already, first reader responsibility to down the database means once first reader enter into database, no writer should come, right? That is the reason I am the first reader. If RC equal to 1, what should I do? So I am performing now down on, okay. So down on dB, I will perform down on dB, this understand, down on dB. Okay. So suppose I made down on dB equal to 1 assumption, down is successful. So no writer will come. Then should I allow the what readers or not? Then I should allow the readers. How to allow this one? The fourth point you understand here, this work is over. Then first of all you have to up mutex, up mutex. If I do up mutex, what happens you see now. First reader assumption, first reader came, mutex value 1, 1 down 0 successful. I increment RC equal to 1, RC value 1, so dB value initially 1, 1 down 0 successful, I made it. Then up mutex, mutex value 0, make it 1. So in this step if I do, then other reader, suppose reader R2 came assumption. So down on mutex, mutex equal to 1, 1 down successful, I am making R2 equal to 2. So if R2 equal to 2, the RC value 2, so 2 not equal to 1, condition is false, we are not looking this one. Then up mutex, mutex becomes 0 to 1, then third reader can come. Now n number of readers comes now. The fifth statement is going to be, this is the critical section. So now reading this your database. So read what? dB, right? So read the dB like this one, okay. So n number of process can enter into this database. So writer, suppose, so n number of process in this database assumption. If writer tried assumption, what happens? Writer code will be here, right? So now writer process comes, so dB value what? 0, 0 down, 0 down, it is a 0 blocking. So writer is blocked, readers are coming now. So once reading of database is over, the process has to leave, process has to leave. So now sixth statement I am trying to write here, the sixth, how to leave it. So while leaving you should decrement your count value. So again you perform, so like a down on mutex, so down on mutex, why sir? Because RC is a shared variable, right? So you should be treat like critical section, right? So down mutex, then you should decrement RC equal to RC minus 1, yes or no, RC minus 1, then so keep on going, right? So what should be 8th statement, please understand. So keep on process going on, like leaving from the database, what? Readers. So last reader responsibility, what is the last reader responsibility? RC equal to 0, right? When RC equal to 0, you should what? Make it up dB, so that other writer or reader can try, freshly they can try. Then ninth one, once this done, last one, you should what? Up mutex, up mutex. Suppose, so I am making up, okay, up mutex. So mutex I am taking like this, up mutex here, okay. Suppose sir, now example, there are 10 readers assumption, 10th reader means 9th reader only. So when I decrement, RC becomes suppose 9 assumption, RC value not 0, we are not going to update, simply you are making what? Up mutex, so that other reader can come. So I will be closing this one. So this open and close, right? This open and close like this. So I repeat this part like this. So this is not there, right? So simply you can close it like, close it, fine. Because you can put it while one, so always true, like a number of times this can run, or only one time can be run. So this is what? Writer code and reader code, writer and reader code. Let's understand this, what you can see, the tracing part you can understand here. So tracing part you can understand here, tracing or analysis, okay. Analysis, okay. Suppose ready queue has concurrent environment. I am taking scenario reader 1 and reader 2 and reader 3 assumption, and writer 1 is their assumption. 3 readers and 1 writer is there. Let's take the scenario how. So it is going to be ensure mutual exclusion, those things will observe. At time t0, suppose example reader 1 is allowed assumption, okay. Reader 1 tried. So reader 1 will read like work this code. So first of all down on mutex, also taking mutex value, okay. Initially mutex value 1 and initially dB equal to 1, correct or not? And initially RC equal to what? 0, right? This is initial data. Now the first statement down on mutex. So first statement down on mutex. So the mutex becomes 0, right? What is second statement? What is second statement? Increment the RC value. So I incremented RC becomes 1, correct or not? Then RC equal third statement, RC equal to 1, down dB. The third statement is what? Down dB means this becomes 0, correct. this becomes 0. So now up mutex, the mutex became 1, the fourth statement, right, fourth statement. Then fifth statement what? So reading the database only, right? So reading the database, okay, reading the database assumption. The fifth statement is what? Reading the database. So during this reading the database assumption, if preemption is occurred, I am taking single core processor. If multi-core processor, other process may be scheduled also, but single core processor are taking the scenario. If like R2 is scheduled assumption, R2 schedule. So R2 means it will run the first. So what is first? Down on mutex. So mutex will currently 1, 1 down 0 successful. The second statement increment RC, RC becomes 2. The third statement check the if RC equal to 0, no, RC equal to 1, no, RC value 2, condition false. The fourth will not run, fifth will run. What is the fifth? Up mutex, the mutex becomes 1, correct or not? So mutex becomes 1, then it is entering into where? So sorry, fifth is what? Directly. So fourth will run, sorry, directly fourth is running, right? The fourth will run and fifth what? Entering into database, right? Reading here. So during this execution preemption occur at time T6 assumption or T8. So reader 3 entered. So now down mutex, mutex value 1, 1 down 0 successful. Second statement increment RC, RC became what? 3, RC value became 3, right? RC value 3 became like 3. Then third statement, what is third statement? Third statement condition is false. The fourth is what? Up mutex and entering into what? So DB, it is also reading. Simultaneously, like simultaneous nothing but, so one by one concurrently they are reading what data, but they are in all three process in like database or not, all three in critical section or not, all three in critical section only. So in this moment suppose preemption occur at time T12, suppose writer started, writer. So writer is started assumption. Does writer will go inside the critical section or not? You should understand. What is writer code? Down on DB, okay. DB value how much? 0. So 0 down, this value is 0 only, right? So I am running the statement 1 for writer. 0 down 0 nothing but it's going to be block it or not, block or not. 0 down 0 unsuccessful operation should block. Writer got blocked here. Now later suppose if I schedule R1, R1 was in critical section, right? It will complete the database. Then after completion database, what should I do? This after reading, then down on mutex, mutex value 1, 1 down 0 successful. Decrement RC value become 2, RC value current 3, it become 2, then RC equal to 0, then update. RC is not 0, simply mutex up mutex becomes 1, then R1 over, R2 comes, down on mutex, mutex equal to 1, 1 down 0 successful, decrement RC becomes 2, so RC value is not 0, just perform mutex here. So mutex up 1 becomes, then so now RC will right now 1, so only R2 also completed, R3 also completed database, then reading database over, then perform the down operation mutex value 1, 1 down 0 successful, then decrement RC becomes 0. If RC equal to 0, then up DB value becomes what? Up value DB equal to 1, then mutex becomes 1. So now leaving from the database, so next writers or readers can try. So this way I can give a solution like based on the semaphore for reader writer problem. I hope you understand the semaphore based solution for the what? Reader writer problem. Okay. So just you can verify the code here. This is the way we should write it. Then now let's see some questions. Let's see some questions on the semaphore based one which were asked in earlier GIT papers. So we'll observe it. Question number 1. Consider the following solution to the producer consumer synchronization problem. The shared buffer size is n and 3 semaphores are the empty, full and mutex defined with the initial values to 0, n and 1. 0, n and 1. Semaphore empty denotes the number of available slot in the buffer for the consumer to read from, and semaphore full denotes the number of available slot in the buffer for the producer to write it. The placeholder variables denoted PQRS in the code given below. Assigned either empty, full. The valid semaphore operations and wait and signals are there. Now he is given a code, producer code, and this is the consumer code. Now he has given which of the following assignments of PQRS will yield the correct solution. So where is the PQRS? No, here wait P, okay, wait signal Q, wait R, signal S is there. In place of R and S, PQRS, we have to fill it. Only two options you have to fill it. Either fill what? full or full or empty only. Na? So there is again, so assign either empty or full to this one. By reading this code, you should recall in a session number 2, I discussed the solution for producer consumer problem by using what? Semaphores. Like I used the counting semaphore, binary semaphore. Based on that problem only, they have framed the question, simply modified. So producer code, like it might be produce something, you perform the wait operation P and wait operation mutex, add the information to the buffer and signal it and wake up. Then consumer also, so first before consuming you perform the like semaphore operation on this one and consume item and signal it. This is the code is there. So now here essential thing you should understand, what is essential thing here? So there are 3 variables are there, empty, okay. There are 3 variables, so empty, okay. Empty and full. So empty, full and mutex. So mutex. What are the values they assigned? You should understand. Mutex are defined with the respect, initial values are this is 0, this is n, this is 1. We should understand. Empty 0, what is the meaning of empty 0? And also semaphore empty denotes the number of available slot in the buffer for the consumer to read. So this related to consumer, This is for related to consumer process. This is related to producer problem, and mutual exclusion to ensure this one. Full equal to n nothing but there are n full slot. So there are, you understand, available slot. The full equal to n nothing but, you understand, there are n empty slots in the buffer or available slot in the buffer to produce you place item. So these same variables I use in case of producer consumer problem, but meaning are differently given. There in that problem, empty defines number of empty slot for the producer I given, and full is indication the number of full slot in the buffer for the consumer, but he reversed here. So now empty is acting like a full is acting like a empty. That should understand. Here empty equal to 0 is nothing but there are 0 slots, there are 0 items in the buffer. Empty equal to nothing but there are 0 items in the buffer, so you cannot consume anything. Full equal to nothing but, you understand what is full equal to? There are n slots available, there are n empty slots available to place the information. The reverse you should understand. So accordingly you should place it now. What should I perform? So just recall the code which we discussed that time. So what we did that time, please understand. Empty for the producer, right? Empty for the producer. First you decrement like down on empty, down on mutex and place item. Correct one. Now here is reverse like. So now here what should I write in case of this one? So in case of P, so I should perform wait, okay. So wait, generally down on empty I did, right? You should do what? Down on reverse, full I have to do, correct or not? So down on full one I should do, because full value how much right now? N, full equal to n. So when you place item, number of full slot, empty slot will reduce, right? N empty slots are there, which are assigned to full. When I place information, now n reduced to n minus 1. So full value is n. So that is the reason you should perform wait on full. Reverse you should do. Then you wait on mutex anyway there. Then signal mutex. This is signal mutex. Then signal what? So this, what is the Q operation I perform? Signal. So when full is reduced, nothing but empty will increase, right? Yes or no? So empty value was 0, it will become 1. Then similarly for consumer, so when item you want to consume, so number of items should reduce, right? So now wait on which operation I have to perform. If full empty is increased, nothing but empty should reduce, right? So down on empty or wait on empty, then here is going to what? Signal. So signal on what? Full. Signal on full, like this you should write it. So in case of P full, Q is what? Empty, and R is what? Empty, full is what? Like S is what? Full. So full empty, empty full, full empty, empty full, full empty, empty full. Which option is matching? In case of P full, then empty, this here empty and full. So option C is matching or not? Option C is matching. So this way you can answer. If you know that code, like if you analyze the producer consumer problem, like with semaphore with solution, answering such question becomes very, very easy. This question was asked in the GATE paper 2018 for 2 mark question. I hope you understand the solution. Like anybody having any issues, So try to comment in the video, so that definitely will resolve it, all of you. So now let's move on to next second question. Consider procedure below, for the producer consumer problem which uses semaphores. Again, no semaphore. So producer consumer problem with the semaphore based only given. Some producer code is given, consumer code is given. Now they are asking which of the following statement is true. There are 4 statements given. So based on this code, they given this like statements, we should answer which statement is correct. Statement 1 saying that producer will able to add an item to the buffer, but the consumer can never consume it. Never consume it. Producer can place, consumer not able to consume based on the code. Maybe say modify the code here. The consumer will remove no more than 1 item from the buffer. He is saying that only 1 item can be removed by the consumer. Option C says that deadlock occurs if the consumer succeed acquiring the semaphore S when the buffer is empty. When the buffer is empty and consumer started working with consume the item, so deadlock is possible. This is also we need to trace out. And the starting value of the semaphore n must be 1, not for 0, deadlock free operation also they are asking. Let's understand what observation you can make it. So first of all, you check producer can able to produce more items or not, and consumer able to consume the items or not. Let's also start the case number 3. If consumer is started, really is leading to deadlock. So like this, these are the observation we do it. Suppose look at this producer code. Okay, semaphore n equal to 0 and semaphore another one yes. This is sorry ma, there must be space s equal to 1. Okay, produce, suppose I scheduled producer while true. So produce item, semaphore wait on S. S value how much? 1. So 1 down 0 successful. This is successful. Add information buffer added. Like semaphore signal on S. So now S becomes 1. Signal on N. So N value initially is 0. So this becomes 1. Correct or not? Suppose if I repeat one more time, because while 1 is repeated. Then produce a second item. So semaphore wait on S, S value right now 1, 1 down 0 successful. I can add information to the buffer. Then what? Semaphore signal on S, S becomes 1, N value signal, this is becomes 2 like this. So now if I continue, it can fill n number of items like based on the buffer size. If buffer size is n, so n items able to produce. So we understand producer can produce n number of items. Let's take keep on produce 100 items. After that preemption is occurred for this and consumer started. Let's see now, let's see about consumer. Will consumer able to consume more than 1 item or not? We should observe it, so that we can eliminate some of the options. So right now understand this is repeated n number of times. Preemption happened after some items are produced. So consumer started. While true, semaphore wait yes, yes value right now 1, 1 down 0 successful. Wait on n, n value maybe suppose I place 100 items, n value might be 100 because keep on what is incrementing. N is not anywhere decreased, only incremented is there, like signal only there. So now decrementing, let's take 99 assumption. Remove 1 item from the buffer. Signal yes, yes becomes 1 and consumed. Then repeated. Semaphore wait on yes, yes value 1, 1 down 0 successful. Wait on n, n becomes suppose 98. Remove the item from the buffer. Signal yes, yes becomes 1. So consumed. So I can able to consume n number of items or not. N number of times I can repeat until this n becomes what? 0. Once n becomes 0, then definitely is going to be block the process. So some option I can able to eliminate. So this is one observation. Okay. So with this one, producer will able to add an item to the buffer, but consumer can never consume it. So consumer also can able to consume it. Wrong. The consumer will remove no more than 1 item. So I can able to consume more than 1. Wrong. So now we have to see this one, these cases. Let me try first only, like initially, so no information is the consumer only started first assumption. So consumer only started, initially s equal to 1 and n value initially 0, correct or not? Now let's try first consumer, then producer will see. So while true, semaphore wait on yes, yes becomes 0 successful, wait on n, n becomes what? -1, n becomes -1. Now this got blocked, consumer got blocked because it's negative. Let's say producer started now. So while true, produce one information got produced now, Wait on S. S value currently how much? 0. 0 down minus 1. Minus 1. 0 down minus 1. So this is also blocked, right? This is also blocked. Correct or not? Hence. So now see. The deadlock occurs if the consumer succeed in acquiring the semaphore S when the buffer is empty. So we have started with the empty buffer, consumer started execution. So deadlock is occur. Option C, right? The starting value for the semaphore N must be 1 and not for 0. Deadlock free operation is telling. He is saying, and initially should be N value should be 1, not 0, so that deadlock will not occur. Let's take N equal to 1, S equal to 1 assumption. Consumer started first assumption. So wait on S, S becomes 0, successful. Wait on N, N value initially 1, assume 1 down 0, 0, successful. Remove from the buffer, this operation get failed because no item in the buffer. No item in the buffer. Then signal S, S become 1, consumed. Then suppose second time repeated. So signal become S became 1, again while 1. So S equal to what? 1 down 0, successful. Now wait on N. N value how much now? Already it was 1 reduced to 0, now 0, 0 down, 0, blocked. Then producer comes, it get blocked or not. Now understand, if N value 1 also if you take N equal to 2 also, if consumer started executing first, so there is a possibility of deadlock. Once N becomes 0, consumer becoming blocked, thereby producer also going to be blocked. So this statement going to be incorrect now. 2014 set number 2 mark frame, right? If you know the basic structure of producer consumer problem and semaphore based solution, so any number of questions framed on this area can able to understand or not, because just you need to observe the code and trace out it and observe the statement. Obviously you are able to select the correct answer. I hope you understand the solution for this. So quickly we will move on to another question. Let's take another question here. Question number 3. 3 concurrent processes X, Y, Z execute 3 different code segments that access update the certain shared variables. Process X execute the P operation on wait semaphore A, B, C, D. Okay. And process Y execute the P operation on semaphore variables B, C, D. And process Z execute the P operation semaphore C, D, A before entering the respective code segment. After completing this execution of this shared code, each process invokes the V operation, the sub operation, signal operation on its 3 semaphores. All semaphores are binary semaphore initialized to 1. A, B, C, D are binary semaphore initialized to 1. Then which one of the following represent the deadlock free order of invocation, invoking the P operations by the processes? Deadlock free operation. They given the options. Process X, these are the operation, process Y, process Z. What is the correct order of placement of the semaphore operations so that deadlock will not occur? So I also discussed when I given a solution for the producer consumer problem like based on semaphore operations. So in a part number 2, session part 2, you should watch it. I have interchanged the 2 statements. Then we traced out, we analyzed, so deadlock got arise. Why, sir? I also mentioned clearly, if the order of operations of semaphore, if semaphore operations are not placed order, is bound to lead to a deadlock. So that problem can, that application, that code can lead to what? Deadlock when preemptions are occur. So now they are asking us to select, so the proper order of invocating the P operation of this three processes so that deadlock will not occur. So now let's observe what they are doing. These processes X, Y, Z. So they are doing something, certain code shared variable, certain updating some shared variables they are doing. So process execute the P operations. Let me write it like this. Suppose, so take the scenario. This is what critical section assumption. This is what critical section. So X is a process like X process, right? X process. Followed by Y process, Y process, Y process. Followed by what? Z process, Z process. 3 processes available. Okay. So they are invoking the what? Binary operations like semaphore operations. So X is invoked which operations? So wait on semaphore AB, DC, ABC, and Y is performing what? BC, BC and D, BC A and DRM, like BC. I think it must be ABC only, ABC only, like ABC followed by BCD, like let me write like ABC. So P of A, okay, followed by P of B, followed by P of let me check X operation for forming an A, B and C only, A, B and C, this is C, okay, C. Similarly for Y I am looking Y operation, Y process, right, Y process, B, C and D, P of B, P of C and P of D, P of D, okay. Z process, Z, where is Z? Z execute the P operation semaphores, C, D, A, C, down on C, down on C, down on D, down on A, like this, okay, down on A. So this executing like no, to execute the critical section, processes should use the semaphore operation, successful, okay, like successful execution of this semaphore operation, so enter into critical section, like this given right now. So which of the following, like which of the following correct order will results what? No deadlock, like this they are asking statement, correct. How to understand this one, sir? Like let me take this scenario, first option A, B, C, B, C, D place, B, C, D, A, B, C and C, D, A is there, C, D, A is there. So I am trying to follow option A. Let's work out option A will give it correct order of execution or not. How to understand, sir, this one? So now read concurrent environment, ready queue has 3 process X comma Y comma Z, okay. At time T0, suppose process X as scheduled assumption, process X is scheduled. So thus I am writing operation 1, operation 2, operation 3 like this. It is also 1 and 2 and 3, this also 1, 2 and 3 assumption. So now X has done one operation, okay. So one more thing you should notice, like this whatever order you placing, right, whatever order you placing, that order of semaphore operation should not lead to deadlock, though preemption occurred any moment of time and any number of times. Preemption can occur, that is the case. Sometimes normally without preemption if you run it, so is some of the options, some of the order also can give correct, but always may not be giving. We have to check for if preemption is occur any time, any number of times, still the order of a semaphore operation should not create what? Should not create deadlock. So deadlock is possible when multiple semaphore operations are placed to access what? Critical section, right. So let's work out them. So X started with down on A. What is initial values of A's? So let me also write here. So A initially 1, B also initially 1, C is also initially 1, so D also initially 1. So 1 down 0 successful, right, 1 down 0 successful, statement 1 more. Let's take situation preemption is occurred here, assumption, preemption occur. Then at time T2 suppose yi schedule, process Y. So process Y run the first statement, down on what? B value how much? 1 down 0 successful. It is also preempted assumption, this error indication preemption. So at time T4 suppose I schedule what? Z process, it will run the first statement. Down on C, what is C value? 1 down 0 successful, it is also got preempted assumption. At time T6 process X came assumption, X, it will run the second statement. What is second statement? Down on B value how much right now? 0 down, what happened? 0 down 0, so this got blocked, so unsuccessful operation got blocked. At time T8 suppose Y is scheduled, it will run the second statement Y. What is Y value? Down on C value right now how much? 0 down 0 only, so this unsuccessful operation, this also got blocked. So taking the scenario at time T10, so Z is placed, Z process Z, second statement will run. What second statement? Down on D value what? 1 down 0 successful. So already X and Y are blocked, ready queue having only one process is already scheduled, it can run. The second statement successful, third statement I can, what third statement? Down on A value 0 down 0, this is blocked, this also blocked, correct or not? All three process blocked or not? All three processes are blocked. So now this case is nothing but, you understand, this situation was deadlock only. All processes went to secondary memory, deadlock. So deadlock happened, or all processes went to secondary memory. So no process able to wake up this blocked processes. This scenario we can say deadlock. So now this order of invocation is incorrect. It is leading to deadlock. One important point you should notice, all of you, please understand, sir. So like there are 4 options, is it required to check all options? Is there any shortcut method? Is there any like approach, small observation, so that quickly we have to eliminate some of the options so that we can get an answer? So all of you, my dear students, small little observation on this semaphore operation helps to minimize your time. Some of the options definitely you are able to eliminate. Some of the options you are able to eliminate so that you can minimize the time to answer the question. So what is this observation, sir? Suppose multiple semaphore operations are there. When multiple semaphore operations are there, suppose I am performing A here, then B assumption. Other process may be performing B, then A is there. Okay. So how to understand? If A followed by B is there and B followed by A is there, this order of invocation definitely leading to deadlock. Because what happens here? A down 0, then B, like preemption occur, B down 0, then B is not allowed, here A is not allowed. So definitely this is going to be create a what? Deadlock. So now this logic we can apply. So this logic can apply so that we can eliminate some of the option. So now what is creating now? A to B, B to A is forming a circular point. Let's understand the scenario. Options you see now. You can see the option D. A, it is there, like A and BC is there. A, BC is there. And C, B, D is there. C, B, D is there. And here is what? C, D, A is there. So what is the logic I told you? Did you remember? If first operation is here and last operation here, here is a first operation, last operation, and B is happening where? Suppose example, if you make it down 0, A value 1, 1 down 0 successful. After that this process started, it won't allow it. That you understand. Okay. One more thing. If you run this one, C equal to you are making just 0, you are not able to allow this one. Suppose it is complete B equal to 1, then it is won't allow it. Are you getting my point? Suppose, so this already blocked nothing but this, will it enter? Like, so you try it. Suppose what I am trying to say, if A is there, A equal down, A equal to 1, 1 down 0 successful, preemption happen, it will make C equal to 1 down successful, preemption happen, this is going to block it. Then among these two, will it enter or not? Suppose if schedule B equal to 1 down 0 successful, if preemption happen, B equal to 1, 1 down 0 successful, 1 down 0, so no, B equal to 0, already 0 down, this got blocked. Then if you try already C value 0, so you are going to block, so all 3 processes are going to block. So definitely I can say option D also creating, option A both are creating a deadlock. So look here for our option C. It is what is scenario? B, A, C is there. Then for process Y, C, B, D is there. For process Z, A, C, D is there. Now see, something you should find the relation. So this is there, this opposite is there, definitely creating a problem, correct or not? So this is there, creating a problem. So what is the one more thing? C and here, suppose this last operation, second operation, this also will create a problem. So option C definitely what? Creating a deadlock. Hence, option is the right answer. So what I'm trying to say, what you do similarly, option B points you keep and run the code, trace out the code by applying the preemption for after every instruction. Check whether it is leading to deadlock or not. Definitely I'm telling you, this option B is not leading to deadlock. It is the correct order of semaphore operations. It is not leading to deadlock. You can also compare. There is no such a relation between these operations. So this way you can solve the question now. So I hope you understand the tracing part of the code. We'll see one more question based on this semaphores. Okay, let me take one more question here. A shared variable x in slice to 0 is operated on 4 concurrent processes w, x, y, z as follows. Each of the process w and x read x from the memory increment by 1, store it in memory and then terminates. This x and y is doing process W and x are doing. Each of the process y and z read x from memory, decrement by 2 and store it in memory and terminate the process. Each process before reading x invoke the P operation that wait on counting semaphore S and invoke the V operation signal on the semaphore S after the storing x to memory. Semaphore has initialized to 2, the value 2. What is the maximum possible value after all process complete execution? They are expecting maximum value. So now let's understand. So there are 4 process concurrent process are W and X, WX, Y and Z. Okay. What they are doing? They are performing the like down on S here. Okay. So down on S followed by what this doing? Reading now. The first operation what read? Okay. Read X value. Okay. The second one what? It is incrementing X equal to X plus 1. X plus 1. Third one is what? Store. Store in memory of X only. Then perform what? So V of operation, right? V of X, this one. So this also same thing. P of S statement, you have to read of X, then you should increment X value and store this X value in memory. Short form I am writing, that's it. So V of which operation? V of S, right? So V of S. This is the code, right? So Y is doing what? Perform the down operation on S. The statement 1, you should read the value of X, and second statement what? X equal to X minus 2, decrement by 2. Third statement is store this X value in memory, correct or not? Followed by V operation on S. Z is doing again down on S. Statement 1, read X from memory, and statement 2 again decrement X equal to X minus, so minus 2, right? Then store this X value into memory location, perform V of operation on S, right? V of S, correct or not? This is the code. Verbal statement given, so I written in a code. Concurrently they are running. So what they are asking now? What is S value currently? The S value equal to 2. S value 2. Semaphore binary counting semaphore 2. So now counting semaphore we read. Okay. Now when S value 2 means 2 successful operation can be carried out. That means 2 process successfully you can allow to enter the critical section. Where critical section shared resource is there. So more than 1 process, like 2 process can go because S equal to 2. The positive value of counting semaphore defined, those means successful operation we have seen, correct or not? So now meaning when you are allowing more than 1 process into critical section, there is a possibility of printing what? So multiple values for this shared variable X or not. You are not getting the unique value, you are getting the some value. That is the reason they are asking what is the maximum value of X is printing. What the operations doing? Reading X, increment is also incrementing, and these 2 are decrement. If I run sequentially, what happens? Initial X value is 0, this making 1, this making 2, this making 0, this making minus 2, correct or not? If I run W, X, Y, Z sequentially, you will get what? Minus 2, correct or not? If I run Z, Y, X, W, X, reverse if I run, this make minus 2, minus 4, then increment what? Minus 2 only will get. But so why we will get, why will get different value? Because of, during incrementation, preemption can happen. Please understand, X equal to X plus 1 is not protected. X equal to X plus 1 is not protected. Because if the W process enter into this while performing this incrementation, in middle preemption can happen, another process can enter because semaphore value 2 process simultaneous can be in a critical section. So that value can change. That is the reason they are expected. Suppose S equal to 1 is given, please S equal to 1 is given. So very easy question, this is very easy question. Simply whatever order you run, minus 2 is the answer, correct or not? Minus 2 answer, because if suppose this run first assumption, unique operation if it is there, assumption. So like this is protected, S equal to 1. So when S equal to 1 down 0 successful, when you perform no process comes here, this will make minus 2. This will run if it is minus 4, then this 2 if you run minus 2 only will get. But because of S equal to 2, we can get what? Different values. So what is the clue I am giving to solve this question? To get maximum value, I should protect the increment processes. I should protect the increment process. What you have to do? Either you start one of them. Suppose you started this one. So you are reading x value, right? Incrementing before storing, please. Before third operation, incremented. So simply I should not write x equal to x plus 1 here. So like let now directly. So increment I'll write. So increment, okay, increment x by 1, and third one store x in memory like this. So increment, decrement you can write directly, decrement by 2. So decrement by 2, okay. So register level it will happen, decrement by 2, register level will happen, right. So what I am trying to say, increment, x value increment in memory, so register, before storing in memory location x, preemption applied, apply preemption this one. Then process x comes, read the value, okay, read the value, which value? You are reading what? So you complete, first let you complete this one, x value what? 1, you are reading x value 1, increment what? Is become register level what? 2. Before storing 2, you complete y and z, they make what? -4, then you update this one. So you will get answer is 2, maximum value it will print what? Answer is 2, that's why you have to do it. So I hope you understand the solution, what I am trying to say. Let me work out, So x comma, like I am taking w comma x comma y comma z, these are the processes are ready queue, right. At time t0, if I schedule like a process, if I schedule the w process, to get the maximum value, I will go with the first scheduling what positive values, or if we schedule other things also comes, but there are many cases, right. One case I am taking, so where I want to get the maximum value, I will start with the wx only, w first statement, initial x value almost 0, okay. So when I run this one, read x value means register R1 0 comes. The second statement, increment nothing but this value becomes 1. Third statement nothing but you are updating memory location 1 like this, complete it. At time t4, suppose x is schedule assumption, the instruction 1 read, so register value comes x value here, x value 1 comes here. The second statement increment this value. Before storing here is just suppose apply preemption occur assumption. At time t6 like y, process y started, instruction 1 read the x value into register, let's take register 3, we are storing 1. Then second decrement by 2, this become -1. Store nothing but you are making what? -1 here, -1 you made it. Y completed. Suppose T8 Z came, instruction 1 read the x value into register, let's take R4 register -1. Statement 2 decrement, this become what? -3. Then third statement store, this value become -3 now. At time T10, then leftover process in a ready queue what? X only. What x to do? Third statement store the value. What is store the value? Value is 2. So when I run this one, the value going to be stored 2. So now maximum x value going to be printing how much? 2. This is a case you understand. Suppose if I ask what is the minimum value it will print, sir? Maximal is 2. What is the minimum value printed? When s equal to 2 is here. So one more thing you should notice here while doing what happened here. For you perform the down operation, yes, right? Do not forget this one. So s value initially 1 down 0 success, this one, can I run this one? After that we are making, so sorry, s value initially 2 down is 1. After w running, this again becomes 2 only, correct? And why, sir? Because you see wake up, like no, we are perform v of s also, right? We are perform v of s, s becomes 2 back. Then when I run, when I preempt it, it is not perform the wake up operation, s value 1. When s value 1, then this moment s value 1 becomes 0. Then after running this one, s value becomes 1. After running this one, s1 value first starting point, the s value is 0. After running, s value become 1. They are making what? 2 like this. So there is no effect on this one because one process only extra will be there. So my question was now, if I want to produce like no, I'm asking what is the minimum value it will print it when s equal to 2. Such case you understand first minimum value nothing but you should go for negative. Let's start with the y you start. So y make it what? -2. Complete the y operation. Then you start z. Before storing the value in a register -4 comes. Then you run w and x completely. That changes the value. Lastly you store the value that become -4. So now if I ask you a question, the maximum value will be what? 2. What is the minimum value it can print? In another year we can expect minimum value. What are the possible value if I ask it? So -4 it can print, -3 it can print, -2 possible, -1 possible, 0 possible, 1 possible, and 2 also possible. These are the possible values it can have. So different year, different type of questions we can expect on the concurrence area. So I hope you understand, the solution for this question. So what I'm recommending all of you, go to the first 2 videos, try to understand implementation of counting semaphore and binary semaphore, and see these 2 case studies I have taken. One is like producer consumer based problem and reader writer based problem. For this I given a solution and we have solved some questions. Then you take up the additional previous year gate questions and work out. So you will feel definitely comfortable on in this topic. And also subscribe our channel so that like future whatever videos and notification you will getting, so that that get your beneficial. So this I want to discuss it. And similar way, so one more question, like just you capture this question was asked in GATE 2024. Apply your concepts, work out, you will get one of the option you can capture. So like this is a kind of homework you can say, because easily you can solve it, because this purely based on the previous knowledge only you can work out. So now for what IMS is going to be provide, so you understand, so IMS features you see, so IMS is having the 3 types of module. One is classroom, the offline classes, as well as hybrid model. So you can attend the classes online or even offline, like offline batches we are running in Bangalore in 2 centers, one is Jayanagar, other is what Malleshwaram, even Vijayawada also offline center. So this is a first and second, and third one is a purely online is there. So around we will be providing more than 800 hours content, whether it is offline or online. Apart from this, the classroom teaching and online teaching, there will be 12 personalized mentorship programs will be there. So where the student get interact the faculty to get the better guidance and so whatever challenges is facing during this GATE preparation, the throughout year the mentors, the faculties are going to help the student. That is one important aspect the IMS has. Apart from this, you see, when it comes to test is various test is provided to the students, like chapter level, the concepts level, where also we start with the beginning, the basics, and moderate and advanced level questions, followed by the multi-subject questions, subject-wise questions, and definitely full in the test series where the student can feel the real examination, real GATE exam, having around 12 the mock test will be there. And apart from this, there are we conduct the lot of the YouTube sessions, so giving the information to student, some marathon sessions, revision sessions, like formula based things. There are many exercises we do it, so that definitely this is going to help the student. So to get even more insight about this IMS, you can book your session for free counseling. And apart from this, you can also follow the Telegram group, in which you will be getting the notification for the YouTube sessions, the various sessions in future we conduct, right? So related like the content, the YouTube session content also will be getting. And also you can see the quiz questions, on daily basis the faculties are posting the questions on different topics, so that you will be engaged throughout the days for the preparation. There are many things we will get it, so you can join our Telegram group. And so do not forget to subscribe the channel, and also you can recommend your friends, so they also get benefited through our YouTube channel. So I hope you enjoy these sessions of 3 sessions I have conducted on semaphore based concept from the operating system. You can watch all 3 sessions. Definitely more insights of the semaphore you will be getting from these 3 sessions, because this is one of the most important topic from operating system. In the future also I'll be taking some other subjects, from computer architecture, some important topics. Operating system comes like computer networks, like compiler design. If possible, I'll be taking some series like concept discussion, problem solving. I'll be try to do the n number of sessions, so that is going to be beneficial for you. So try to follow the channel. Thank you so much, all of you. Thank you so much.